Grazie.
Si sente, dai. Non credo si sente, dai. Okay, we can start with this AJS. It's my pleasure to introduce Luca Gennaioli, and the title of this seminar is Asymptotics of the S-fractional perimeter as S goes to 0. Thank you.
Thank you for the introduction, Simone. So this work is a joint collaboration with a friend of mine, Michele Caselli, in Scuola Normale. And well, the plan of the talk is quite simple. First, I will give you a brief introduction of what is a fractional perimeter and the main idea behind the results, the heuristics. Then I decided to stick to a slightly more transversal topic, which is the Hit kernel on a Riemannian manifold, which I think may be useful also to those who are not interested in fractional calculus. And then in the last two sections, I'm going to present the result we obtained with Michele. So let us start with the introduction. Probably you all know what is the perimeter. Perimeter is just a measure of the boundary of a set. Its definition can be introduced via the total variation measure of the characteristic function of the set. And well, you can also define its local counterpart is the relative counterpart, which is basically the perimeter of a set inside another one. All these notions are local because to compute the perimeter, you just need to know how is the set very close to the boundary. And instead, for what concerns the fractional one, as you can see, there are some non-local components appearing. For example, you are integrating over the complement of a set. And so you need to know what your set is also at infinity, let's say. So an heuristic of the result, I hope this is what will remain to you, because the rest is quite heavy from the point of view of the computation. So, well, you all know that the volume is an n-homogeneous function of the radius. So the volume of a ball scale, like you know. And the same goes for the perimeter, but with a different dimension, of course, because of dimensional analysis. For the fractional perimeter, you have a similar scaling, but to a different power, and the power is n minus s. So at least formally, when s is going to 1, you see that the lambda to the power n minus s approaches the one of the perimeter, behaves like lambda to the n minus 1. While when s goes to 0, which is the case we are going to discuss, it behaves like a volume. So yeah, the heuristic for the result is, if you want to perform some asymptotic, you should expect that the perimeter behaves like a volume in the limit. How to introduce these concepts in a Riemannian manifold? Well, what you do is you have to, of course, give a meaning to the singular kernel that you have for the fractional perimeter. And how to do that? Well, you just note that the fractional kernel can be written as an integral of the Hit kernel, which is the solution, the fundamental solution of the Hit equation in Rn. And so to introduce it, you just do the same thing in a Riemannian manifold. What you do is you replace the Hit kernel of the manifold of Rn with the one of the manifold. And in a similar way, you can introduce the fractional perimeter of a set. So these objects actually require the study of an important operator, which is the fractional Laplacian. As you can see, the perimeter is of a set. The fractional perimeter can be interpreted as the HS seminorm of a function, where the function, of course, is the characteristic function of the set. There are several definitions for the fractional Laplacian. The ones we are going to use here are the three you see on the slide. So the first one is the definition via integral of the singular kernel. Then you have the Bochner definition with the Hit flow, and finally the spectral one. Okay, now this is not really rigorous because the first one I'm evaluating pointwise and the other ones are functional. But let me just mention that these definitions in the end, are going to be equivalent in our setting, so I don't want to insist on that. So now let's come to what is the Hit kernel on a Riemannian manifold. So if your manifold is compact, and for me it will always be connected and geodesically complete, what happens is that you can solve heat equation with the initial datum and Neumann conditions, so the normal conditions, the natural boundary conditions. And the heat kernel is the solution of this equation with initial datum, which is a Dirac mass, in the sense that, I mean, as in the limit as t goes to 0, in the sense of measure, you converge to the Dirac mass. If the manifold is not compact, and I see we have a problem with the slide, sorry. If the manifold is not compact, what you do is you basically take an exhaustions with compact sets, one contained into the other, and on each of them you solve the problem with the Dirichlet boundary condition, so that you have a sort of ordered solutions, which is they are monotone one to respect to another. In fact, we have the following proposition, which is, I don't know, probably Grigorian was the first proving this. He proves that basically these solutions are ordered and increasing, so that you can take the limit as k goes to infinity, and you basically get the heat kernel for the whole manifold. Now, this is one of the possible ways where you can introduce it. I chose this because it was simpler to present. Now, some properties which may be well known for most of you. So first one is symmetry. Of course, if you change the variables, nothing changes. It's the same as the Euclidean one. Then you have the positivity, and this is due to the infinite speed of propagation of the heat equation. And then you have the property number 3. I mean, I couldn't choose a name, but I think it's right to say that mass is not created. I mean, this means that if you start from a delta, which is mass 1, you cannot increase the mass. And property 4 is actually the semigroup property. I won't say much more because I think you all know. And property 5 is, well, it's just an expression of the solution via of a general solution with a general initial datum. In Rn, it will be the classical convolution with the fundamental solution of the heat equation. Now, I would like to discuss so small time behavior and large time behavior of the heat kernel. And the first of the two is actually, the philosophy is very simple. So you're studying basically small time behavior means that, okay, your mass has diffused in all the space, but it's really close to the Dirac delta from where you started. Therefore, you should expect a behavior like the one in Rn. And this lemma is saying exactly in a quantitative way what I've just said. It says that, well, if you start from a delta and you integrate outside of a ball, so for small times, all the mass is inside your ball. So outside there is very little mass. And I mean, as you can see, in an exponential way, you go to 0. And okay, the proof is done by drawing in the next slides. So you start from a delta at time 0, which is really peaked. And then after some times you smooth it out a little bit. But if you stay really close to the center, then I mean, you see that the mass outside is almost 0. Now, I would like to, this is for what concerns the small time behavior. For the long time behavior, the situation is much more complicated. And we need first to talk about harmonic functions because they are really related to the behavior at infinity of the solutions of the heat equation. So it's a known theorem of Yau, the one who tells you that if you have an L2 harmonic function on a Riemannian manifold, then it has to be constant. Of course, if the measure is infinite, then it has to be 0 because, I mean, constant functions are not in L2. And so we presented a proof which is tailored also for singular settings. And actually, Nicolò, who is online now, told me that he proved with the Mondino a result even in a more general class of spaces. But for our purposes, let's stick to the Riemannian manifold setting. So you have a function u which is in L2, and its Laplacian is 0. Then you flow the Laplacian via the heat equation, and this remains 0, of course. Then you commute the Laplacian with the heat flow, and you use the fact that this solves the heat equation to get that the derivative in time of your solution has to be 0. Therefore, for every time you are a constant function in L2. And now you would like to prove that this function is 0. How do you do? Well, by standard theory, regularity theory, or gradient flow theory, if you want, the gradient of the solution is in L2. So you can now integrate by parts. So the Laplacian goes, I mean, half of the Laplacian goes to the other side, and you get the L2 norm of the gradient. And this is 0 because the Laplacian of the solution is 0, we saw. And therefore, this allows you to conclude that V is constant. But being V constant, since you converge to your initial datum as t goes to 0, this means that also the initial function has to be constant. Now, the L2 setting somehow is well studied, well known. Much more complicated is the L infinity setting. So there are manifolds indeed where there are L infinity functions or bounded functions which are harmonic but non-constant. For example, the hyperbolic space. And the construction is quite complicated, so I won't speak about that. But the question is there any geometric or interesting property that enforces this L infinity Liouville property to say L infinity Liouville means you are bounded and you are constant? So the answer I present here is partial. It's not due to us. It's well known. So one of the possible assumptions is that the Ricci curvature is non-negative. If that's the case, you have basically some property due to the heat kernel, for example, which allows you to infer that any L infinity solution has to be bounded. Sorry, I'm distracting for the noise. Any harmonic function which is bounded has to be constant. Yes. I don't know. I have to check. Is it fine now? Maybe remove it. So yeah, we were saying the L infinity Liouville property is enforced by non-negative Ricci curvature or by the volume growth. So the second one is a proof due to a Cacciopoli type inequality, basically, which forces the gradient of any bounded harmonic functions to be 0. And well, of course, that's nice. What is interesting for us is that if you have a Riemannian manifold and a set with infinite volume, infinite measure, then you have these properties on the solution of the heat flow starting from the characteristic function of the set. Maybe you take a set, you flow it with the heat equation, then you evaluate the solution at point P and you evaluate it at point Q, you make the difference, then this has to go to 0 as t goes to infinity. So this is a consequence of the L infinity Liouville property. As the limit at infinity of solution of the heat equation are stationary solutions, so Laplace equals 0 basically. So this was some preliminaries for introducing the problem of the large time behavior of the heat kernel. So for large time, the heat has spread out all over the manifold, so it's not local anymore. What you expect, it has to capture some global properties. Indeed, it's really well known in the literature that if the measure of the manifold is not infinite, so it's finite, then the heat kernel converges locally uniformly to 1 over the measure of the manifold. This is easily seen in the compact case. In general, it's more complicated. But what we proved, and remarkably, we couldn't find it in the literature, is actually some sort of, let's say, natural continuation of the result, which is if the measure is infinite, then the limit has to be 0. Because you formally put, instead of the measure of m, you put infinity, you get 1 over infinity. So, at least formally, it's true. How does the proof work in the case of finite measure? So basically, you use the theorem of Yau that I showed you before for the L2 case. So you use the spectral measure representation of the heat semigroup. Now, this is, maybe I won't say too much about this, but I just want to point out that by dominated conversion, the exponential kills everything. Except for lambda equals 0, where you have a delta, because of course a 0 is always an eigenvalue. And you have a delta, and there basically you converge to the projection onto the space of harmonic functions which are in L2, which is the space of constant functions. So you have to convert to what you see. the semigroup he converges to the integral of u over the measure of the mean of u, basically. It's the mean of u. So, and for what concerns, this is a weak convergence. Now, the formula 2 actually gives you convergence of the norms. So since you are on uniformly convex space, so an Hilbert space, you get strong convergence in L2. And to get local uniform convergence, I will explain it later, because first let me deal with the case infinity, which is really the same. So the measure infinity is really the same proof. Just when you project into the space of L2 harmonic function, you get 0, because there is no L2 harmonic functions, which is not 0. Therefore, in this case, you converge strongly in L2. And now to translate these properties to the it kernel, you just use the semigroup property. And after that, you apply basically a local Harnack inequality, and you control the L infinity norm with L1 and then L2, and so you get local uniform convergence. So this was everything I wanted to say for what concerns the it kernel. Now I would like to speak about the result we obtained. So for the finite volume case, it's really, I mean, didn't require all this talk about the it kernel maybe. So the first result in the setting, in this setting, is actually due to Pallara, Carbotti, and other people. Basically, they work just with the Gaussian space, which is Rn with the Euclidean norm and the weighted Lebesgue measure with the Gaussian. And basically, we prove that every manifold with finite volume, actually we prove any weighted manifold with finite volume, has to have this behavior of the asymptotics as s goes to 0. So as I told you, the asymptotic, you should think that it should behave like a volume. And in fact, in the result, if you see the limit, I mean, you just have volume terms, right? So now in this slide, since it's quite technical, I will cheat a bit, of course. And okay, I will just stick to the case of the full perimeter. I will not talk about the case of the relative one. But I mean, as I told you, the result is really a volume, and it's really non-local because it appears also the volume of the complement of E. So, and so sketch of the proof is basically you start with the spectral representation as usual. Okay, maybe you are more familiar with the discrete case. So think of it as it was a discrete case, so that the spectrum is discrete. And basically, you just perform the asymptotics for functions U, which are in HS. And what you do is you take the limit and you get, okay, the first one, as you can see, this term here is like the Fourier series by Plancherel theorem. This is the L2 norm squared. And this one, as I told you before, is E0 of U has to be the projection of U into the space of constant harmonic functions. So it is the mean of U. Therefore, you get this additional term. And okay, the asymptotics is just put instead of U, you put the characteristic function of the set, and you get the limiting result for the characteristic function of E. Note that at least formally, you should expect that in the infinite volume case, let's say, this term should disappear because the measure is infinite. So if you put infinity, the denominator should just remain with the L2 norm squared, at least formally. And indeed, for the infinite volume case, that's basically what happens. But before discussing that, I need to introduce the notion of angle at infinity. And maybe I will make a little draw. So basically, you want to compute the angle at infinity of a set. So we are in a Riemannian manifold of infinite volume. So it's non-compact. And what you do, you take your set, which goes to infinity. Then you take a ball. And you integrate the singular kernel outside. So you integrate this guy. And this sort of gives you a renormalized angle in the sense that, for example, if you take exactly a circular sector of angle alpha, and so this is E, then theta of E is actually alpha over 2 pi. This is in R2, of course. So the idea is that this quantity captures the angle at infinity that your set makes. But actually, it would be more appropriate to call it density. We will see later why. And well, basically, if it exists, because actually there are sets for which this angle is not, doesn't exist, because, for example, sets that oscillates a lot, maybe this limit doesn't exist. In fact, it doesn't sometimes. But this is for sure bounded by the angle of all of Rn, basically by monotonicity of the integral. So what really happens is that in this case, the angle of Rn is 1, of course. And you notice that these quantities, if they exist, they don't depend on R, on the radius of the ball that you're integrating with. I mean, you're integrating the complement of the ball, no? And it doesn't depend on that. And it doesn't depend on the point. In Rn, it's easy to see because you make a change of variables. But in the general case of a Riemannian manifold, it's more complicated. And to introduce the angle, however, it's very simple once you remember what we did in the beginning. You just replace your singular kernel with the Ks, which is your new kernel. And you just have to know that, I mean, Ks, at least locally, looks like the one of Rn. And so you perform basically the same analysis and you ask yourself, but then, I mean, what happens now? Does it depend on R? Does it depend on the point? I mean, it's not so easy because you cannot change variables anymore like before. What you can say, though, is that, I mean, to solve this problem, you need to introduce the notion of a stochastically completeness. And what is a stochastically complete Riemannian manifold? It's a manifold where you don't lose mass. You let a Dirac delta evolve and the heat flow preserves the mass. So the integral of the kernel is 1. And more in general, actually, you know that the function taking t and returning the mass of the kernel is monotone, non-increasing. I mean, at least, I mean, if you don't want to, the proof is really short, but the point is that you don't create mass, so it cannot be increasing. With these notions, now we can state our first result, which is in the infinite volume case, if your manifold is stochastically complete, actually, if and only if the angle at infinity is 1. And so I said heat density because actually you can interpret this quantity as a measure of how much the heat flows at infinity inside your set. That's why I called it heat density. And okay, briefly, the proof is really simple with the tool we just built. So you assume your manifold to be stochastically complete, and you divide basically the quantity you are going to take the limit of in 3 pieces. One contains the small time behavior of the kernel, which is the first one. The second one contains the, say, middle times, and the last one contains the large time behavior. So for the first one, it goes to 0 because you have the exponential convergence for small times, if you remember. So everything is super integrable, and it goes to 0 because inside of the kernel, actually, maybe I should have pointed this out, but inside this kernel, there is a constant which scales like this to make the asymptotic analysis, because otherwise, I mean, also at infinity, you see that, okay, this kernel is not singular at infinity, but if S goes to 0, then it becomes singular. Therefore, you have to renormalize it to make the asymptotic. And for what concerns the middle times, you just apply I mean, I would call it maximum principle, but basically the fact that if you start with an L infinity solution, you cannot increase the norm. So the norm is preserved. And since you are flowing the characteristic function of a set, which is the complement of the ball in this case, your solution has to be smaller than 1, basically. And so basically, so these 2 terms go to 0. While for the last one, it's a bit different. You use the stochastic completeness. You really use it now. You break the integral over 2 contributions, one over the ball and one on its complement, and you substitute inside your integral. Now, the first integral is just a computation, and I can tell you it's 1. Hope you trust me. And the second one is actually the convergence of the kernel we saw in the case of infinite volume manifolds, because this solution is the integral of the kernel over a ball of radius r. But the kernel goes to 0 uniformly, so this guy goes to 0 uniformly, and therefore in the limit as s goes to 0, you have to get you get 0. So this was the first arrow. Actually, if theta of m is 1, you also get that the manifold is stochastically complete. Why? Well, the first two pieces are zero no matter what. Doesn't matter stochastical completeness. It's just, one is the local time behavior of the kernel, and the second one is the fact that it doesn't increase the infinity norm. It's just the third one, the problematic one. And so if theta of m is 1, you automatically get that the third integral has to be 1 for every t. And okay, by a contradiction argument, now I don't want to enter maybe too much in detail because it's really just technical. You get that theta of m is less than 1 if your manifold is not stochastically complete, and therefore you reach a contradiction. So, but now the point is, okay, this is for theta of m, so the angle at infinity of all the manifold. What happens for a set, for a generic set, like those ones I drew? Well, it turns out that the quantity theta of P and R actually does not depend on R under any circumstance, but it may depend on P. It does not depend on P if your manifold has the L infinity Liouville property. So if bounded harmonic functions are constant. And again, I mean, this is just with the tools that I told you about the kernel, it's really easy to prove this because, okay, first you notice that basically it doesn't depend on the radius because theta for bounded set is 0 because theta captures the behavior at infinity. So if your set is bounded, it really, you get 0. And basically it's just it's an easy computation where you break in the various terms again, and they all go to 0 for the usual reason, the first two at least. And the third one goes to 0 again because of uniform convergence of the kernel. So the kernel goes to 0, you get 0 again. Therefore, we can compute it for the ball of radius 1, this angle. So you integrate over the complement of a ball of radius 1. Independence on the point is a bit trickier, as I said, but again, the computations are, I mean, it's straightforward once you understand that it's the infinity Liouville property, the one who drives the asymptotics. Basically, you can prove that you can integrate just on the complement of the Polar radius 1 centered at P instead of the one centered at Q, because well, you just put them in just one set, basically, because bounded set don't give any contribution. And once you've done this, you just need to prove the last limit, that the last lim sup is 0. So what you do is you expand your singular kernel via the definition with the hit kernel, and you use the infinity Liouville property to be sure that this guy inside goes to 0 as t goes to infinity. And once you've done that, basically the proof is done. So we now have the asymptotics for the infinite volume manifolds, and well, I will not discuss again the case of relative perimeter, but just let me mention that again it is non-local, and again you have volume terms, but you see that this time this theta makes its appearance. This quantity theta, I did introduce it for a reason. And I mean, what happens is that in the case of the standard perimeter, or now you don't see maybe because of the bar, but you converge to the measure of V. So what you get is really the measure of V. And at least formally, you get this result again because, okay, if you consider that the asymptotic was this one, in the case of finite volume, if E is bounded, okay, maybe you need an approximation argument, but basically you can't result somehow because the complement of a bounded set is infinite measure. Okay, this is just heuristics. And what happens though is that this is actually true. And again, the proof is the same. I mean, follows similar steps as in the case of finite volume, but you have to prove pointwise convergence of fractional Laplacian. And okay, to prove that, you have to make some sort of analysis of the latter operator. And okay, I mean, you take a function with the compact support, infinitely differentiable, and you just run the computations. As you can see, or maybe you cannot see because of the bar, which I cannot remove now, the last term is actually theta. You cannot see, but it's m. Maybe it's okay, good. It's m. You are integrating in the complement of the ball of radius r. So that quantity there is theta of m. It's really theta of m. So you could actually perform the asymptotics also if this guy was not one. So also in non-stochastically complete manifolds, but let's not enter into that. And okay, I mean, now since u is smooth, you can do basically whatever you want. So you break the integral inside of the ball in two pieces. One where ux and ui are really close. So where x and y are really close. So you choose, I mean, this row small enough, and the other one outside. So what happens is that, okay, it's easy to see that the first one you bound with the Lipschitz constant times the distance function. And the second one you just bound with the two times the L infinity norm times the integral. Now you get that the second is 0 because if you see the second is basically in the limit is theta of a bounded set, of course in the limit. And so this has to be 0. For what concerns the first one, as I told you, this kernel behaves locally like the 1 over n. So if you stay with x and y really close, you can prove that this kernel really goes like a power of the distance function. And the power is the right one, because when you put this inequality in place, what you can do is that you can apply co-area formula. And with co-area formula, basically you get an integral over R of the perimeter of the set over, I mean, this kernel, the distance function becomes the radius. And I mean, if you use the fact that your manifold locally looks like the Euclidean space, the perimeter of a ball goes like R to the power n minus 1. So you just substitute this guy inside the integral. And what you get is, of course, a convergent integral. And in the limit, this goes to 0 again. So this proves that the limit is 0, and it also proves the theorem. So maybe now, so some open questions are, we actually couldn't understand really what the L infinity Liouville property is related to. If it is like, what are the geometric conditions that really capture this property? We don't know. We thought at the beginning that maybe you can also prove that if theta doesn't depend on the point, then you have to have the L infinity Liouville property, but we are not able. Maybe it's not true, I don't know. And well, of course, another question is the asymptotics for S going to 1, because at the beginning I show you, you should behave like a perimeter. So in a render is this result, I think is due to De Filippis, Ambrosio, and Martinazzi. So maybe there's hope to reproduce also that. And I mean, with this, I'm done. Thank you for your attention.
Thank you, Luca. Nice seminar. Are there any questions? Maybe I have a question. Can you go back to the definition of the angle of the set? Can you explain if there is a relation with the blowdown procedure? If it is the density of the blowdown?
Yes, somehow it should be, yes.
But if it is, then I don't understand.
But yeah, sorry.
I don't understand why it should exist. I mean, if the set E oscillates.
Exactly. That's, in fact, it doesn't exist in that case. I mean, yeah, actually, I mean, I thought you were talking about the whole space, but no, for a set, it doesn't need to exist. Because of what you said. There are a counterexample is exactly made of a conical set which oscillates right to left, and they proved it in the paper of Figalli that this set does not admit this limit. So theta of this set is not computable. Yes.
So your set is what property as you see?
No, my set. I mean, depends. I mean, you want to like so. The existing theory is one thing. The fact that if you exist, then you do not depend on the point and on the radius is another thing. What we do is we assume that it exists, but then maybe it depends on the point, on the radius. That we just take care of that. We assume it exists. We have in a Riemannian manifold. There are many probably sets for which this limit does not exist yet.
Okay. Yes.
Maybe I don't remember exactly. You told that hyperbolic space is a counterexample to the L infinity.
Yes.
Okay. Because you also said that for Ricci non-negative, there are no problems, basically because it's finite mass in that case.
No, negative Ricci is not finite mass necessarily.
Not necessarily.
No, because you have cylinders. So non-negative Ricci is not a problem because okay, at least this is a way I see it, but then maybe there are other ways. But basically, if you take your function u, which is in L infinity, and you compute this L infinity norm, okay, you can prove that this is smaller than a constant, which, okay, in general, it's dependent on the curvature. Okay, I will write you the general formula. So, it's something like this. Okay. So as you can see, if the curvature is greater or equal than 0, this guy at infinity doesn't give you any problem. So this guy instead sends everything to 0. So when you flow your harmonic map, what you get is that in the limit at infinity, you must get 0. But I mean, if you flow an L infinity harmonic function, so what you get is herself. So this proves that since when you take the limit is 0, this proves that the gradient of u has to be 0. And so u has to be constant. Yeah. So this is why in the Ricci case it's like this. And for the other one, it's basically an estimate of this kind. So it's really it's a Cacciopoli type inequality where you have, I think, something like this, maybe without the square here. The point is, if the measure of, if you remember, the condition was this one. Here you bound with the L infinity norm, and measure of the ball of radius r over r square goes to 0, and so this guy has to be 0. Yeah.
You can perform with the theory for massive spaces.
Yes, actually we can, but it's a bit over. Actually, you can perform. I think you can perform it in much more general settings, because when you see the proofs, you just need some estimates on the kernel, existence of the kernel. So maybe you can work also on more general setting. But then there's a problem of fractional Laplacian. You have to prove that the definitions are equivalent, which is not so easy. So for the RCD setting, everything should be true because you have Gaussian bounds. But then, it's complicated, I guess. Yeah. So we prefer to stick to the, volume manifolds and manifolds, okay, RCD, okay, but then, yeah, we didn't investigate further, let's say, yes.
There are not, thank you.